So the last thing that we're doing, what's different about this function compared to what we've been doing so far in this unit? I'll give you an idea. What we were doing before was things like y equals e to the 3x, or y equals 5 to the 3x. And then that's an exponential function. This thing here that we're looking at isn't an exponential function. So certainly not logarithmic. So what does it have to do with logarithms? An exponent, I mean, there is an exponent, but it's not an exponential function. Exponential functions have a number for a base. Yeah, good observation. This is unlike anything we've ever seen because it has an x both in the base as well as in the exponent. So what do you think we're going to do? Anybody have an idea? Why would we do that? But why? Why is that helpful? There's a very specific reason why that's helpful. And then one other question I would pose to you. You're right, that's what we're going to do, so we can do that. We're going to take the log of both sides. Which base do you think we should use? What's the easiest base? This is what I'm talking about. Like sometimes you get to choose the base. Huh? No. No. That would be interesting. It doesn't really necessarily make sense because then that would like clear things, but yeah, base e, because that's the easiest derivative. So in other words, we're going to take the ln of both sides. So let's do that. Whoops. Ln of y equals ln of x to the 3x squared. Now that we've written it out, do we notice why this is useful? We can bring this amazing property that we've talked so much about with logarithms, that you can take an exponent out of the exponent and bring it down as a product in line with the rest of it. So that's exactly what we're going to do. So this ends up being 3x squared times, ln of x. There is no other way to do that. Well, no other, at least easy way. There probably is another way, but like people might try to do something like this, something weird like this. Well, I'll use the polynomial rules. So I'll bring the exponent down front and get 3x squared, and then times x to the 3x squared, and I'll subtract 1 from it or something like that. Like this doesn't make any sense when you're doing it with variables in the exponent. So people would make something up and try to do something like that. But that is very, very wrong. So it turns out there's this thing called logarithmic differentiation where there are cases, and we're going to look at a couple today, where it just makes life so much easier, or it makes it even possible to take a derivative by taking the log, or log base e ln of both sides first, simplifying a bit, and then taking the derivative. Okay, and that's what we're doing. That's what logarithmic differentiation is. So we're going to go ahead and do that. What do you notice about this question before we move forward with now taking the derivative? I think it's simplified as it's going to get, so we can take the derivative now. What do we notice about it, though? A couple things. It's implicit, exactly. It is no longer an explicit function. It started explicit, but it's not anymore. And then on the right side is product rule, but hopefully we're on the ball with that now. So when I take the derivative of the left side, what do I get? What is the derivative with respect to x of ln of y? Not quite. Is that? Yeah, 1 over y. And then times the derivative of y, which is dy by dx, that thing that we always need to have in there. Then it's derivative of the first thing, which is 6x times the second thing, plus derivative of the second thing, which again, I wouldn't usually write this out. I'm doing it just so people can follow the lesson if they're looking at it after times the first thing, 3x squared. Then we always solve for dy by dx, and the first step almost always looks the same with these ones, because I'm just going to multiply both sides by y. And I can do a little bit of cleaning up here. By simplifying the x in the bottom here with one of the x's in the 3x squared. And there's one more thing that we were not able to do in the past, but we are now, so we're going to do it. Again, this is just to illustrate to you that this is something you can do in some cases. We've not been able to do it up to this point. We were always told to leave our answer in implicit form in the past, and the reason was because you were doing questions that were something like cos y equals sine of x plus y, or something like that. You know, maybe plus 3xy. Well, you can't solve this for y. This is implicitly stated because it's not y equals, and good luck trying to rearrange this to be in explicit form. I don't think it would have an explicit form where it just says y equals. So you have to leave your answer in implicit form. But in this case, the question that we're working on now, you don't have to. We know what y is. We have an explicitly stated expression for y. It's right there. So generally speaking, in these questions, you would sub y. And I would say it's probably a habit where if you can, then you do. We couldn't in the past, so we didn't. Now we can. So moving forward, you know, you would ask, well, do we have to? Well, I would say yes. If you can, you probably are supposed to. These questions, generally speaking, aren't ones that we're really worried about doing stuff with. I think in the practice today there is one where you're finding an equation of a tangent line or something like that, but like generally we're not really worried about how we're factoring, because this is factorable and I could do some other stuff with it, but I'm going to leave it like this because that's not really what we're worried about or interested in this process. That being said, we're going to look at some different examples today where, you know, we are going to sort of simplify and see how they clean up, just because it's good practice and it's good to notice things and observe things and think about how it might simplify in case you have to. Why would we want to put it into explicit form? Why is that useful? Why would that be, generally speaking, a habit? Any thoughts? To answer that question, I would think to myself, what are the kinds of things we do with derivatives? Find critical values. And it might be easier to solve for 0 with one variable in it rather than 2. Very nice. Any other reasons? What else do? We find equations of tangent lines. We find slopes of tangents. At when x equals 4, if I have it explicitly stated, I can just sub 4 in for x and solve without worrying about what y is. You may have to find y anyway, but you know, so it maybe is a little bit simpler. Dealing with one variable usually is simpler if you can. So we're going to make a little note just because I want to have it copied down. If you're here today and you're not asleep, you probably won't forget this, but I want to be as explicit as I can. Whoops. So when you have a variable, of course in this case x, but it could be any variable, of course, but you know, generally speaking for us it's x. When you have a variable in the base and the exponent, we're going to use logarithmic differentiation. So we're going to take the log of both sides first. Which is logarithmic differentiation. Take the log of both sides, then take the derivative. It's implicit, but it's simple. And in some cases, it allows us to find derivatives that we couldn't have otherwise. And in some cases, it's just easier. Any questions? So take the log of both sides first, simplify to get that exponent down, and then you can take the derivative. All right, let's try a few. Like, it depends on what you're doing. Again, I mean, I think that that you could kind of do some stuff with x's there, but in this case, we're not overly worried about how we're simplifying it. That being said, if the instructions in the question said factor fully, that's what you would have to do. Some of the test will say factor fully, some of it will say first line only. If it says first line only, it's not worth simplifying. It may not be easily simplifiable or nicely simplifiable, so we don't touch it. So take the ln of both sides. Take the derivative, and we notice that this derivative looks the same every time. And we have product rule again. Does anybody remember what the derivative of cos of x is? Negative sign. So derivative of the first thing times the second plus derivative of the second, which is 1 over x times the first. Something like that. And again, you know, we rewrite it explicitly because we can, and to show you that that's something that can be done, what that looks like, and there are cases where you might want to. But in this case, like, it's not that helpful. Like, it's not like I can simplify further and start putting, like, you know, a lot of the time these functions are pretty messy things. X to the cos of x. How are you going to simplify that? You know what I mean? So it's not really helpful. We're just showing that you can do it. That make sense? Questions? Is that one done? Okay. Try this one. I don't think there's anything too tricky about it. When you go to take the derivative, you got to remember one little thing, so it just challenges us a little bit further. So when I go to take so I've taken the derivative of the first part times the second plus the derivative of the second. So what's that going to look like? That's going to look like 1 over 3x minus 4. And then chain rule, you have to take the derivative of the argument of the logarithm as well, right? So times 3 and then times the first thing. And I see that there's like, a 12x squared that you could factor out of both parts there. But I'm going to leave it like that. You good? Questions, questions, questions? One more like this, and then one more that's a bit different. Go ahead and try it. Whoops, I went too far there, didn't I? Ln of y equals. I haven't actually started taking the derivative. That's better. Okay, now go ahead and try. So I get a bit of a mess here. Let's see how we can clean this up. So I have this 2 and this 2. And then I have 1 over root x. And then I have another 1 over root x. So you wouldn't have to write this out twice like this. And then I have that x left. But I'm just showing you what I'm doing. So this ends up being root x times root x is x. So this is x over x. Kind of nice. Yep.
Isn't the original function just x over x?
No.
2x over 2.
Is the original function x over x?
X over x.
Why? Let's finish this. So what can I... So again, a lot of people I think would leave it like this. Well, you'd get x over x is 1, but you'd leave it like this. But what else can we actually do? So I'm going to replace y. That useful property of logarithms that allows me to take the exponent out, sometimes it's useful to put it back. And in this case, what would that look like? So that cleans up very nicely, and the square root of x all squared is just x. But again, you're going to sit there and be like, do I have to know how to do that? I mean, not necessarily. Leaving the 2 out front would, if you were using this for something, that wouldn't be all that harder to leave the 2 there. Wouldn't be that big of a deal. But what I'm saying and what I'm thinking is you do want to just start looking for those kinds of things. Like, it's helpful to you. It's useful if you notice those kinds of things. It'll make your life easy. And in fact, coming back to what you said before, what was the observation that you made? So we could have done something similar using exponent laws, before. So, or could we have done y equals, so this would be the square root of x squared all to the x, because you would multiply the exponents together to get 2 times x, which is 2x. And this actually ends up being x to the x. Well, does that make it easier? Like, is it worthwhile? So ln of y equals x, ln of x, 1 over y dy by dx equals the derivative of the first thing, which is just 1 times the second thing, plus 1 over x times x. So I would tend to say, yeah, that was easier. But you got to notice it. Maybe you do, maybe you don't. It's a good lesson not to get too caught up or hung up on if your solution answer doesn't look exactly like the answers that we post. Because somebody else who did the solutions may have simplified first. And that might cause it to naturally work out a little bit differently. And it's not your job to necessarily make your answer look exactly like what someone else does. Now, if it's simplified fully, generally speaking, they're all going to look alike. But even then, not necessarily. So how would you know if yours is right? I think this is a good tool that you can use going into university as well. Find a website, like Wolfram Alpha is a really, really powerful website, really good one to use, and start learning how to type these expressions into something like that to see if they're equivalent. Type yours in, type the solution, the answer that's posted online, just say this equals this. It'll come up and say true, or it'll come up and say no. And if it's no, if it's not true, your answer's wrong. If it comes up and says true, the expressions are equivalent, so your answer is correct, it just looks different. Questions, questions, questions. So here's one more. Kind of a big one. You've never done one quite like this, but I thought it would be a good challenge for you, practice. So you've got 36 minutes. Hopefully you can get it done before the end of the period. Or Stephen, did you want me to show you an easier way to do this one? What do you think? Huh? You think, would that be nice? Because this would be hard. Quotient rule with a product rule on top and a product rule on bottom, and every single one of those has like power of a function going on, chain rule stuff like, oh, this would be a doozy. By the way, I think this 3 is in the root sign. This is a cube root of that. Well, what are we doing today? We're doing logarithmic differentiation. Why would taking the log of both sides be helpful in this case? I don't know, but I have a hunch that's what we're supposed to do because that was the title of the lesson. So let's see what happens if we do that. Well, it didn't help yet. What can we do? Yep, and so because it's a quotient, it's the top minus ln of the top minus ln of the bottom, but then we can also separate all the products. And can't we turn it into this? Ln of y equals ln of 3x plus 7 to the 4 plus ln of the square root of 9 minus x squared minus ln of e to the 4x minus ln of the cube root of x squared plus 1. And we can take it a step further. Bring all the exponents out. What is this? Ln of e to the 4x. It's just 4x. That's nice. That saved a lot of trouble. And this is a cube root, so it's 1/3 times the ln of x squared plus 1. Now, I'm not saying taking the derivative of this is going to be fun, but I think it will be a lot easier. Oops, those are gone. Still a bit of a mess, but way better. And then I would, I suppose, sub y back in, but, and this would go here, and this would be y. But not very useful. Like, so rewrite in explicit form, if you're told to, if that's what your instructions were, of course you do that. But like rewriting that disaster, it's not very useful. Any questions? If a question like this popped up on a test and you did it the other way, but you did it correctly, unless it said use logarithmic differentiation or something, I suppose you might get full marks, but you might run out of time. And if you did it the other way, your solution wouldn't necessarily look like this. Like if I was going to factor this, I got a bunch of things that I need to start doing common denominators with. So it would still be a bit of a disaster. Like it would be messy, right? But that's what you would do. But I don't know what that would ever model in the real world that you would actually have a function like that. But so for us, it's just good practice. Any questions?